Hello, so in today's video, I'm just going to summarize all of the statistics facts that you need to know before your paper 3 stats. If you're an AQA student or an Edexcel A-level student, so you've got your paper 3 on Tuesday, and it's going to be stats involved in that, whether you're AQA or Edexcel, both of those examples will have stats in it. So this is a summary of all the stats that you need to know. So the first point I'm going to make is remembering all of your sampling techniques. Remember, you just got to learn these by brute force, unfortunately. So remember, a simple random sample. That's when you've got a population. You're going to give. You're going to use a random number generator to give everyone a number in your population. So everyone's got a number, and then you just randomly use a generator or a calculator to generate random numbers until you've hit your sample size. So it's random because remember what the word random means in maths. The word random in maths means every person in your population theoretically has an equal probability of being selected. So it's just important to remember what this word random means in maths. So random, every person in your population has an equal probability of being selected. So simple random sampling is obviously random. Stratified sampling, that's when you order everyone. So you give everyone a number, assign everyone a number using a number generator, order everyone in ascending order, and then you pick every for example, 10th person or 20th person until you've hit your sample, your maximum sample size. Quota sampling, so this is not random. This is where you put everyone into groups, and then you take whoever you can out of each group. So it's not random. So you basically split everyone into groups, and then until you've got your quota, which is your maximum number of people that you need in your sample. So you select your groups, put everyone into groups. Say, for example, you're going to split everyone into year 12 and year 13. And let's say you're going to take 7 people from year 12, 10 people from year 13 in your sample. You just select whoever you want in your 2 categories until you've got your sample of 7 in year 12 and sample size of 10 in year 13. So it's not random sampling. It's just splitting people into groups and taking who you need. Opportunity sampling is, again, not random. It's literally taking your opportunity when you can. If you see someone, that's part of your sample. So just picking random people, whoever you see. Stratified is when you split people into proportionate groups. So you look at the number of people in your population in each group. So let's say you've got 100 year 12 students, 200 year 13 students, then a third of your sample has to be year 12 students and a third of your sample has to be year 13 students. And then once you've got the number that you need from each strata or each group of people, then you take a simple random sample within each group. So that's kind of how that works. But again, just remember your sampling techniques. Make sure you're also happy with calculating standard deviation. So one by calculator and one by the formula. So remember that your standard deviation formula goes a bit like this. So it's the square root of the sum of all your data squared. So take all your data, square all the numbers in your data, add them all up, take away the number of people in your data, the number of data points you got, times that by the mean to x bar the mean squared, and divide that all by n. So that's how you calculate a standard deviation, and then obviously you square root it to get your standard deviation, because the thing inside the square root is just your variance. You may also see the formula written like this. Some people write it like this: so the sum of your data squared divided by the sum of the square of all your data divided by n, and then take away x bar squared. So you may see that as well. It's exactly the same thing. So remember, x bar is your mean, n is the number of people in your sample, and this x squared is the is when you this sigma, capital sigma x squared, is when you square all your data, add them all up. That's what that means there. So hopefully you've got practice with that using the formulas, and also by calculator. So putting data into a calculator and then getting your calculator calculated. So make sure you're happy with the ways you calculate standard deviation, because that's quite important as well. Also some key probability formula that will be useful. So remember your conditional probability formula. So the probability of A given B is equal to the probability of the intersection between A and B divided by B. So I've kind of drawn some Venn diagrams there just to show you how it works. So the intersection divided by your probability of B. If the letters were the other way around, then you would have probability of A on the bottom of your fraction instead. So just be aware of that. The next formula is this one here. So the probability of the union of A and B, so A or B. So this is kind of how it works. So I've done a Venn diagram to illustrate how this formula works, and this is quite a key formula that I would recommend learning. So everything inside A and B is equal to A plus b and then take away the middle, so the intersection, because you've double counted the middle when you've added a and b together. So that's a key formula to learn. Also, be aware of this one here. So obviously the probability of everything in A and or B, so the union of A or B, plus the complement of A or B, so everything not in A or B, is equal to 1. And just also be aware as well that the probability of the complement of A union B is actually equal to the probability of the intersection of not A and not B. So the reason why this is a kind of try to illustrate it here. So if we think about these two Venn diagrams, A complement and B complement, so not A and not B, where does the blue lines and the red lines intersect? So they just intersect on the outside of these two circles, so outside of the A union B region. So basically the opposite of A union B is the same as the intersection of not A and not B. So that's just a key one as well to bear in mind too. Next, a discrete random variable. So make sure you're happy with how discrete random variables work. So the first point is obviously to remember that discrete data is obviously data that can take a fixed number of outcomes. So a discrete random variable, so it could be, you know, the number of penalties that you score out of 10 chances. It could be, you know, the number of games that you win in a day. So it's a fixed number of a fixed number of outcomes. That's what a random variable is. So when you do something, a random variable is when you've got a fixed number of possible outcomes. So for example, you could have this, you could have a game. So I mean, let's just say you're taking penalties. So X is the number of penalties that you score. So you may score 0, 1, 2, or 3. And then you've got a probability. So the probability you score 0 is going to be f of X. Probability you score 1, g of X. Probability 2, h of X. Probability 3, p of X. So remember that all of these, so remember probabilities add up to 1. So f plus g plus h plus p is going to be equal to 1. Now, this second thing that I've written down here, you actually don't need to know this, but I think it's just useful to know in case something a bit tricky were to come up. Just be aware that the mean of a discrete random variable is basically that times by that plus this times by that plus this times by that, and then plus this times by that. Now in the syllabus, it says you don't need to know that. I would just be aware of that just in case you were challenged in the exam, or just in case they gave you a challenging question where you had to think outside the box a little bit. So that time, so the X values times by the probabilities, add them all up, that's your mean. So just keep mind of that. So now binomial distributions. So remember what the criteria is for a binomial distribution. This is really important. So binomial distributions, you've got a fixed number of trials, M. You've got a fixed probability of success in each trial, P. So fixed probability of success in each trial. And there are two outcomes, success or failure, always two outcomes of a binomial distribution. That's why it's called binomial, so two possible outcomes. And the outcomes of each trial are independent. This is an important one. So the outcome of one trial does not affect the outcome of another trial. So again, it could be taking penalties. If we're going to assume that taking penalties, scoring goals in a penalty shootout is a binomial distribution, then you have to assume that one penalty being scored doesn't affect the probability of another penalty being scored afterwards. So that's key with our assumptions. Remember, we've got this formula as well. I mean, you can get away with not really using it, but again, I'd make sure that you understand it. So remember, the probability that you get a certain number of successes, X. X is your number of successes there, the lowercase x. So it's the number of, so first of all, let's look at the actual probabilities here. So if we want to get X successes, then we want obviously P, which is the probability of success, to the power of X. So probability of success times by probability of success times by probability of success X times. So we want X successes. Also, if we're going to take N, so with our penalty shootout example, if there's going to be N penalties, then that means we want N minus X failures. Yeah, so again, if we want X penalties to be scored, we must want N minus X penalties to be missed. So that's why we include this there. And then this N choose X, or sometimes N choose R, depending if sometimes people use R there. That is the number of ways in which you can order the successes and failures. So obviously, if you've got 10 penalties, you could like score the first 3, miss the next 7, or you could miss the first 7, score the next 3. So there are lots of different ways in which you could order those successes and failures. So n choose x is the number of ways in which we order that, and multiplying the probabilities by this gives us our total probability. So that's how a binomial distribution works. Now, remember the mean and the variance of a binomial distribution. So this is in your formula book. N times p is your mean, n times p times 1 minus p is your variance. So therefore, this is not in your formula book, but just remember that standard deviation is the square root of variance. So you just want to square root that to get your standard deviation. Okay, so next, binomial distribution hypothesis tests. Right, so remember with these hypothesis tests, we're testing whether the probability of success has changed. So with the one-tailed test, we're testing, has the probability of success increased? So again, you're going to read the question, you're going to interpret the wording in your question. Has the probability increased? Or has the probability so do we suppose that the probability has increased, or do we suppose that the probability has decreased? So this is a one-tailed test. So the key thing to remember, if we're doing a one-tailed test with a probability being greater than something, the key thing to note is this. So if the probability of your random variable, your binomial random variable, is greater than or equal to the number of successes in your data, if that probability is less than your significance level in a one-tailed test, we reject H0. So if the probability of getting so many successes, greater than so many successes, was so small that it was less than your significance level, it means that your null hypothesis is unlikely. So therefore, we should reject that null hypothesis, and the alternative hypothesis could be true. So then the next one is if we're doing if we've got an alternative hypothesis where we're testing whether the probability is small. So we've got to do this calculation. We've got to say, okay, so what is the probability that the binomial random variable x is less than or equal to the number of successes we got from our data, which we'll have in the question? And if that is below the significance level, so again, if that's a smaller chance than your significance level, then it means that your alternative, your original hypothesis, your null hypothesis, is probably unlikely because it gave you such a small probability. So we should reject that, and probably we should think about the alternative hypothesis instead. With a two-tailed test, remember that your significance level is split into half. So half of your significance level is devoted to the lower end of your discrete, your binomial distribution. The other half is dedicated to the top end. So remember, if the number of successes that you get from your data is bigger than your mean, then you want to do this calculation here. So you want to calculate the probability that x is greater than or equal to the number of successes. And if that is less than half of your significance level, because again, we're splitting the significance level in half, then we reject H0. So if that probability of getting so many successes and greater than that was so small that it was half of your significance level, you reject H0. And the same kind of idea here. So if the number of successes you got in your data after the question gave you the data, when you calculate the number of successes from the data, if that's less than the mean, so remember the mean for a binomial, remember what the mean was. So the mean for a binomial distribution is n times p. So if the probability of x is, so if we calculate the probability of x being less than or equal to the number of successes that we got from the data is less than half that significance level, then we need to reject H0, because again, this probability is so small that it's unlikely that our null hypothesis was true. So that would be binomial tests. Now let's look at a normal distribution. So with a normal distribution, remember continuous data now. So data that can take an infinite number of possible outcomes. So we got a mean mu and a variance sigma squared, so a standard deviation of sigma. So remember, the probability that x equals something is 0 because we've got continuous data. So there's infinitely many possibilities. So the probability you pick one thing out of infinitely many possibilities is just 0. So remember, the probability x equals something for a normal distribution is 0. The probability that x is greater than something or x is less than something, you can use your normal CD function in your calculator. So normal CD function in the calculator is what you want to use to do that. So hopefully you're all fine with that. Now, if you do not know the mu or sigma value or both in your distribution, so let's say you get a question and they don't give you the mu or the sigma value, then you've got to convert into a standard normal distribution, this Z distribution, the mean of 0 and a variance of 1, and also a standard deviation of 1, of course, because when you square it 1, you get 1. So the formula, remember what the conversion is. So Z is equal to your initial distribution, take away its mean, divided by sigma. So that's your conversion formula. Now, I've just done an example here. So let's say the probability you want to calculate the mean and sigma value for this distribution. So the probability that x is greater than 100 equals 0.1, for example. So that's the same as this here. So the probability that x minus mu over sigma is greater than 100 minus mu over sigma. So remember, what we do to one side of an inequality, you must do to the other side. So I've just done that there. But remember, this thing there is the same as our formula for z. So I've just swapped z with that there. So then what we want to do is now use the inverse normal function on the calculator to actually calculate this value there. So what is that value? We want to use inverse normal because inverse functions tell us values on the x-axis. So just like an inverse function in pure maths, an inverse function tells you this value there. So you're going to go to your calculator, inverse normal. Your area is going to be 0.9 for this example. So why is that? That's because your calculator is programmed to take areas to the left of this value there. So the calculator takes areas on the left side of your normal distribution. So if you've got a greater than sign, which we got here, we actually want 1 minus 0.1, which would be 0.9. Now, if this is a less than sign, then the error will just be 0.1 in your calculator. But because of this greater than sign, it's going to be 0.9 instead. Mu is 0 because mean of a standard normal is 0. Sigma is 1. Standard deviation of a standard normal is just 1. Okay, so now let's go to the hypothesis testing. So with one-tailed hypothesis test with a normal distribution, your H0 is always mu equals whatever it was initially the mean. Sample size of n, let's say you got a sample size of m. Now remember, if each of your data in your sample comes from a normal distribution with a mean of mu and a variance sigma squared, so I forgot the squared there, then you have n lots of this distribution. So let's say you got a sample size of 100, you collected 100 pieces of data from a normal distribution, you've got 100 individual piece of data that come from this distribution. So when you calculate the mean, remember with these normal hypothesis tests, we're thinking about the mean of the distribution. So when we take the mean of all of our data, we're actually taking the mean of 100 pieces or n pieces of normal distributions. So remember what the distribution of the mean of a set of normal distributions is. It goes like this. So it's the original mean and the variance is now sigma squared over m. Again, you don't need to know the details. You just need to know that this is true. If you want to know the details, I'm actually going to do some videos this summer doing like some crossover A-level and university maths where I will go through the explanation to this. But all you need to know for next week's exam is this here. Right, so then with a one-tailed test, so let's say you've got you're doing an upper side one-tailed test, your H1 is mu is greater than. So if the probability of your mean distribution is greater than the mean from your data that you collected from your data or the data in the question, if that probability is less than your significance level, so if it's really, really small, smaller than that significance level, it means your H1 is unlikely, so you reject H0. Same kind of thing here. So this time, if you're looking at the lower side of your distribution, so with a mean less than your original thought, if the probability of your mean distribution is less than the mean from your data, if you calculate the probability of your mean distribution being less than the mean from your data, if that probability is smaller than the significance level probability, that probability is so small under assuming H0, so H0 probably may not be true, so we're going to reject H0. Now, two-tailed tests, so that's when your null hypothesis is mu not equal to something. So if your data, if from your data you collect, so from the data in the question, let's say the mean in the question from your sample was greater than the mu value that you originally thought in your null hypothesis. So again, if the probability that the mean distribution is greater than the data mean that you got from your data, if that's less than a half of a significance level, remember two-tailed test, we want to split the significance level into two. So half significance level down there, so half SL there. And then the other half of the significance level will be split down there. So if this probability is smaller than that, again, we want to reject H0. And same thing with a hypothesis test where we've collected the data and we've got a mean less than the mean we thought it actually was, if your probability for your mean distribution being less than your data mean, if that probability is so small that it's less than half of your significance level, so this area there, then again we reject H naught. It's probably unlikely that the mean was what we originally thought. Okay, so that would be that. Now let's go to using a normal distribution to approximate a binomial distribution. So some students struggle with this kind of question. So the key thing to know is that if you've got a large sample size in your data, and if the p-value is approximately 0.5, then you can approximate a binomial distribution as a normal distribution. So remember, the mean of a binomial distribution is n times p. That's why there's an np there. And the variance is n times p times 1 minus p. That's why that's there. So that's all you need to know. But you also need to know this as well. So you need to know about continuity correction. So remember, binomial distributions, this is discrete data. So discrete data. So we're using continuous data to approximate discrete data. So we've got to do this continuity correction because we're, again, using continuous data to approximate discrete data. So we've got to do a continuity correction. So this is kind of how it works down here. So the probability that your binomial distribution is greater than 100, that's going to be approximately the probability that your normal approximation is greater than 99.5. So why is that? If we think about a number line, let's say we got 100 there, we want the probability that x is greater than or equal to 100. But remember, 99.5 actually rounds up to 100, because obviously 99.5 rounds up to 100. So with continuous data, we want to include the 99.5 as well. Similar with this one down here. So let's say you want to calculate the probability that your binomial distribution is greater than 100. This is approximately equal to the probability that your normal approximation is greater than 100.5. So this time, remember, discrete data, the probability that your discrete variable is greater than 100, this is actually the same as the probability. So the probability that your discrete binomial distribution is greater than or equal to 101, because remember, binomial distributions take whole number values. So therefore, you want to use 100.5 in your normal approximation when you do your continuity correction. So hopefully that will make sense. And the very last point to mention is correlation coefficient. So remember, a correlation coefficient is just a measure of how strong a correlation is when you've got bivariate data. So when you're plotting a scatter graph, a correlation coefficient is 0, means no correlation. Correlation coefficient of 1, this should be a 1 there, is a perfect positive correlation. So all your points in your data lie perfectly on a straight line. It doesn't, the key point to notice, it does not tell you the gradient of your straight line. It just says that you've got a positive gradient with all your data lying on a straight line with a positive gradient. And -1, a correlation coefficient of -1, tells you that you've got a perfect negative correlation with all your data lying on a straight line with a negative gradient. But again, it doesn't tell you the gradient. So it doesn't tell you how big the gradient is. It just tells you whether it's a negative gradient or a positive gradient. And then the hypothesis test, so remember, H naught is always this rho equals 0. And then your alternative hypotheses could be rho less than 0 or rho greater than 0. That's a one-tailed test. Two-tailed test would be when rho, the correlation coefficient, is not equal to 0. So again, the same thing when you've got a two-tailed test, make sure you split your significance level in half. And the key thing to notice is this. So if your correlation coefficient from the data they give you in the question, so the number that they give you, if the modulus of that is greater than the modulus of the critical value, then you reject H naught. So if your correlation coefficient from your data is more extreme than the critical value, so let's say your critical value is down there, so that's your critical value there, and you got something like this in your data there, so that's your coefficient there. Now this is more extreme than the critical value, so it's close to -1. So therefore we would reject H naught because it seems like there could be a correlation. So therefore we can't, it's unlikely to assume that there's no correlation. We would assume that there probably could be a correlation. So that's correlation hypothesis test. So that was a very, very quick, brief run through all of statistics. Hopefully that helped, but any questions, do drop them in the comment section. So again, thanks for watching and good luck with your revision, and hopefully your paper 3 all goes well on Tuesday.